Do you? Awesome. I was just going to say start the recording. All right. Welcome to our February VAST 2025. We had the last 2 months off or so we've been using that time to build a good schedule for the coming year. I remind everyone that if you have interesting software projects that you would like to present, that you should go to our VAST webpage or our GitHub page, file an issue. That's how we take ideas for potential presentations, and we go through those, and then we'll reach out. And we especially encourage junior scientists, grad students, postdocs who are active in software projects to give a presentation. We're very happy to have two talks today. One by Rhys Taylor, who's going to tell us about FRELLED, and the other by Marc, who's going to tell us about the PDR Toolbox. We're going to do those two talks in that order, about 20 minutes each. We'll take maybe a question after each, and then I'll turn things over to Sam, who will do our general Q&A afterwards. The talk will be recorded. If you don't want to appear in the recording, just keep your camera off, and we will post things to YouTube in a few weeks or a month or so. All right, so I'm very happy to have Rhys Taylor, who did reach out via our GitHub issues page to suggest this talk, so it does work. Staff scientist at the Astronomical Institute in Prague, who's going to tell us about FRELLED, FIT's real-time explorer of low latency in every dimension. So a wonderful acronym. And so I'm going to turn things over to Rhys, who will start us off.
I'll share my screen. And I will start. Can you see and hear me and see the screen correctly?
Yes, it looks great.
Okay, great. Thanks. So thank you very much for allowing me to present this to you today. So I am an observational astronomer. I work mainly with single dish H1 data, so generally unresolved sources, mostly from Arecibo. But I also work to a lesser extent with much higher resolution molecular line data from ALMA. And so what this package is, it's something I've been working on since around 2012 or so it's evolved a lot over the years. But the goal was to have a visualization package which would work in a way which I felt was more natural than other options which were available to me at the time. So what actually is FRELLED? Well, it stands for, as you see, the FIT's Real-Time Explorer of Low Latency in Every Dimension. The acronym comes from a somewhat obscure Australian sci-fi of the 1990s. Very few people get that reference, which is slightly disturbing. But what essentially it's a set of Python scripts written for Blender. So Blender, if you don't know it, is a software program developed really for artists. So it's about allowing users to generate landscapes and architecture, spaceships, characters, animations, video games, all that kind of general art content. And back when I had time to do such things, I was quite a dedicated Blender hobbyist. And when I started doing professional astronomy, I realized pretty quickly that, well, if I could just bring my FITS files into Blender, I'd have a much better interface and a much more natural way of interacting with and inspecting my data. So this is something I've been working on to try and bring that idea into a useful format. So one of the key features of Blender is that it really is designed for viewing data three-dimensionally. There are a lot of excellent three-dimensional astronomy packages out there, but there are also a lot of tools in which the 3D component is sort of tacked on. It's sort of seen as a nice bonus content that's like, yeah, you can also look at your data and view it in a nice way, but it doesn't really let you do anything else with it beyond that. With FRELLED, thanks to the Blender interface, the 3D format is essentially integral to the whole process. It really is geared around viewing your data in that way. The other thing that I've tried to do here is to incorporate a lot of different viewing capabilities into the same software package. So you don't have to learn different software to view your data in different ways. The goal is to try and incorporate as many capabilities as possible into this one tool. So to give you an overview of the major features of when you should use it, and of course, when you should probably stay away from it and avoid it, because it's not always appropriate in every situation. Well, it's designed for viewing data cubes in 2D and 3D, and these can be small to, let's say, moderate in size, up to about 1,500 pixels on a side. Not so small necessarily. You can go beyond that, it's just not necessarily recommended. It will allow you to do multi-volume display, so you can actually overlay two volumetric data sets on top of each other. So if you have different chemical species, you can see those different components. You can also do some analysis tasks, so you can create contour plots and various maps of your data in situ in the same viewing area. You can also use it to create, hopefully, presentation quality figures of your data with various annotations. One of the key aspects of this is that it's designed to be astronomer friendly. It's no good, I think, expecting people or astronomers to use Blender in the way that artists learn to use it, because that essentially requires astronomers to become artists, and Blender's learning curve is notoriously steep. So that idea is really a non-starter. What I've tried to do is essentially overhaul Blender's graphical interface completely, so that the only tools you see are the ones that you will actually need as an astronomer. So the goal is you learn Blender as an astronomical tool, not as an art tool which can also do astronomical analysis. The code is open source. You can access that code directly at any time within FRELLED, but 99% of users, I hope, should never need to look at that code at all. Everything should be accessible through the interactive graphical interface. So what can't it do? Well, if you load your data into a traditional viewer like DS9, you can usually interact with your color transfer function, so you can interactively set the data scaling and the brightness and contrast. You only have some limited capability for that within FRELLED. So if you get your data display range wrong, you do unfortunately have to reload your data, which can be rather slow. As I say, you can load cubes which are larger than 1,500 pixels on a side, but performance does drop off quite steeply beyond that. And that is really a limitation of Blender itself. It won't really matter how good your hardware setup is. Blender really can't handle data sets much larger than that. So that is something I'm actively working on trying to work around. Although you can, of course, view numerical simulation data in this, you can view any FITS files, standard Cartesian uniform grid FITS file should load. It's really geared towards observational data set. In earlier releases of this, I did allow it to do some n-body simulation visualization with vector overlays, which are more useful for analyzing numerical simulations. In the course of recoding this for the latest release, I had to drop this because this was just getting too big a task to maintain. Hopefully, I'll be able to bring those features back in the future. It's supported on Windows and Linux, not yet Mac. Your data has to be Cartesian, and it also only runs in Blender 2.79, which is an older release of Blender. Again, I hope to upgrade to a more modern version of Blender, which will be more capable at some point. Okay, so that's probably enough about what the software actually is, but I think it's far more useful to simply demonstrate to people. Well, I'll show you for yourselves what it can actually do directly. So let's start with what it's like to actually visualize your data in FRELLED, except that my screen has got stuck. There we go. So this is an example. This is an HCN cube from ALMA of, I think it's the LL Pegasi region. So this is what it looks like once you've loaded it in. That takes typically, well, this cube I think took about 30 seconds or so to load. And then once you've loaded it, you can interact with your data quite naturally. So you can pan, zoom, rotate. You can dive deep inside your data. You can toggle from orthographic to perspective mode. You can look around so you can see your data inside out or outside in. You can adjust the opacity of your data, which shows how bright everything is. So if you want to see fainter features, you can increase that, and that will hopefully enhance their visibility. Conversely, if those pesky faint features are getting in your way and obscuring the bright features that you're more interested in, you can adjust the clipping so that you can then hide all that noise and you can concentrate on viewing those bright features. Of course, that depends entirely on what your scientific use case happens to be. One of the key points here is, of course, that that viewpoint, as you rotate and zoom, updates almost instantaneously in a truly sort of real-time view at around 25 frames per second or more. As I said before, I think a lot of other packages will let you do some viewing capability, but they often require a significant update time, which can even be a few seconds, even if you make only a very small adjustment. And that prevents you from exploring your data in this more natural way, which I've tried to do with FRELLED. So that's a volumetric display, but you can also view your data if you prefer as isosurfaces, so surfaces of a constant data value. Here I've shown them on that, overlaid on that same data set. Again, you can rotate that view, but you can also simply toggle that volumetric view off so you can see only the isosurfaces. You can see here, though, these transparent isosurfaces you see by default, they have some unfortunate ugly artifacts in Blender. They don't look brilliant by default, but what you can do is toggle their display method to show them as more solid plane surfaces, and then you get a much clearer view of what you can see. The same clipping control that you can use for the volumetric display also works for isosurfaces, so you can hide and reveal faint and bright features depending on what it is you're actually interested in examining. And then, well, of course, the 3D is sort of the heart and soul of the project, but I quickly realized that, well, at some point you do have to use more conventional 2D images as well. So this is an H1 cube of M33 from Arecibo, shown in that standard volumetric way. But what you can also do is simply toggle that to a 2D display, and then you can pan through, for example, the spectral channels here, but also position velocity diagrams along the major orthogonal projections. And those 2D maps are quite good at enhancing the visibility of the faintest features in your data. So in this standard view, what you're seeing here is just that the color is set according to the data values. But one other thing that you can do is toggle so-called height fields or height maps, in which the data value also displaces the data orthogonal to that surface. And so this is quite a useful way of enhancing the visibility or clarity of features in data of very high dynamic range. Again, you can rotate your view around this. One other fun feature, which Blender just has anyway, so I didn't have to code it, is it comes with a built-in flight simulator. So if you want to, you can actually fly around your data in this sort of fighter pilot style fashion. I apologize for my terrible piloting techniques, but hopefully it's good enough to give you the gist of what's going on there. But there is a sort of serious point to this, which is that I'm trying to make data visualization really a sort of fun part of the process. It shouldn't be something that you see as a chore that you have to really think about how to do it. It should be something that's seen as integral to the process of analysis, just as much as the more quantitative aspects which you need for interpreting your data. But also I think height fields or height maps are really valuable because they effectively allow you to show your data with two transfer functions at once. So for example, if we disable those height fields, you can see in this case, the brightest part of the galaxy is, even with this logarithmic color transfer function, is shown as this uniform, homogeneous, saturated blue, because it's just not possible to find a transfer function which shows the faintest and the brightest features all together. With a height field, you get around that. And you saw before that this, what appears as a single value, actually shows two very distinct peaks, which is not at all easy to see using just an ordinary typical color display. Okay, so then a problem that I often encounter with other packages is, well, okay, you can visualize the data, but what next? What do you get out of this? Often I find that they are really capable at showing you a particular feature, but they don't let you do anything with it. And so what I've tried to do is enable FRELLED to sort of balance the capabilities of visualization and analysis. So it's not as specialist as any of the more dedicated tools, but it tries to fill that middle ground, which I think is relatively underexploited. So one feature I really wanted to do from the beginning was to allow users very easily to just catalog sources in their data. So this is a much more typical data set for the kind of thing that I work on. This is an H1 data cube from Arecibo as part of the Virgo cluster. All of these long sort of cigar-like blobs that you see, these are H1 detections of galaxies. And what FRELLED allows you to do is place this 3D cursor just by clicking with the mouse at the position of anything you think might be a source. And you can use this peak cursor button to make that easier. That places this cursor at the position of the greatest data value along the current line of sight. You can also position the cursor in other ways, but that makes it really easy to accurately find the position of a source. And then what you can do is set up what are called regions, which you just press this button to add them, and then you interact and scale those with a keyboard and mouse. These are virtual Blender objects. You can toggle the display between wireframe or solid. You can adjust their color. Normally, when I'm doing this, I just use black, so they're just not visible. And that means you can just go from source to source, creating these regions, cataloging them, knowing for sure if you've already cataloged a source or not. And you can see here, this is really quick to do. It doesn't take long to learn this. It takes maybe a few minutes really to get a feel for how to do this. Not really that much more than that. And at most, it takes typically a few seconds per source. And so here's one I did earlier. This is, you saw me interactively cataloging those first two sources. In total, there's about 98 sources, I think, present here. This took about an hour to create all of these. Under real-world working conditions, you can create maybe 300 catalog sources per working day. You maybe extend that a little bit with some dedication. But what it means is that you can essentially catalog even quite large data sets by eye without using a visual extractor or automatic extractor if you don't want to. But of course, you can also import these regions from an automatically generated catalog. So you can use those two methods in concert with each other, and you can really compare what you detect by these different methods in different ways. Now you can see here I've used different colors to highlight different regions. This can be set arbitrarily per each region. And when you toggle the view into the 2D display mode, you see that as you pan through the position velocity slices, those regions automatically show up. If you create them in 2D or 3D mode, they each show up in the other display scheme. And you see here I've also mixed some regions to be shown as solid with some being shown as wireframe. So what you can do with these, well, apart from simply extracting the coordinates of a source, you can also create interactively various contour plots and maps. So in this example, I've created a set of renzograms for some of these sources. Renzograms are just contours of a fixed data value where the color of each contour indicates the spectral channel. And these have been overlaid with RGB maps from the SDSS. Now you might think, well, in this case, there's quite a lot of sources and they overlap with each other. So some of these maps obscure each other, which looks frankly horrible, but that's easily avoided. There are buttons so that you can simply focus on the selected region, which automatically hides every other region and all of its annotations, and then you can just bring them back with another button. There's a button which does the reverse of that. So if you want to, you can just simply hide one particular selected region if there was only one that was getting in your way. There are various other contour plots and maps that you can generate, all of which are done in essentially the same way. You select a region, you use a drop-down menu to specify which type of map you want, and you press a generate button, and it typically takes a few seconds per source to generate any given map. If you have Myriad installed, you can also use this as essentially a graphical wrapper for the MBSpect task. So you can interactively set the size of a region, and that will determine the spectral profile window, which MBSpect uses for measuring the spectral parameters of a source. And you can show that graphically with an X server window. And you also get the textual output in Blender's window of all the major parameters that MBSpect measures of your source, and then you can save that instantly also to a text file. I think I'm sort of running low on time here, so I'm going to try and wrap this up quite quickly. You can annotate those figures. You can add arrows, and the beam size is generated automatically from the FITS header. One experimental feature is that you can actually export your data into virtual and even mixed reality in later versions of Blender. So you can actually grab that. So this is my hallway. So this is the M33 isosurfaces. You can step around that. You can step inside your data. You can grab it with your controllers and expand it to make it bigger or smaller. It's good for outreach. No analysis features of this yet. And finally, you can also animate the display settings, so you can actually you can set this up entirely through the graphical interface in FRELLED without learning any of Blender's dedicated, more artistic-oriented features. But here, what you see I'm animating is the contour levels of the isosurfaces. I honestly don't know if this is scientifically useful, but it is nice for to present to people what you can do with your display capabilities. Okay, so just so I have some time for maybe a quick question, also I have to mention that it also has a name resolver, so you can find your favorite source very quickly. That uses a standard AstroPy tool. And so that's the gist of it. So the link is in the chat. I'm still, of course, there are always bugs to find, but any feedback, positive and negative, would be extremely welcome. So yeah, thanks for your attention.
Thank you, Rhys. That was very cool. Yeah, I've never used Blender. I've heard it's got a big learning curve, so it's nice to have a project that's dedicated to reducing that learning curve for astronomy. So this looks really nice.
Yeah, hopefully you should just be able to open it and watch the first tutorial, and you should hopefully pick up all the rest of it quite quickly.
Right. Not a question, but I remember you presenting this at ADASS. Super cool idea. Makes me want to learn how to use it and Blender. I'll ask a quick question, Rhys, because I don't know much about Blender, but you mentioned that it's sort of pinned at the moment to an older version of Blender.
Yeah.
I guess that Blender has gone through major changes. Is that the sort of hold up? Is that older version still widely available?
Oh yeah, the Blender is also completely open source, so that version will be available in perpetuity. I certainly hope this version I presented was actually a recode from an even older version, which is now truly obsolete. The Python code that this is written in should be much more easy to migrate to a later version, but it will still take some serious time and effort to bring it up to speed for the later version.
Yeah, I imagine. All right, we're going to have some open discussion at the end. People should drop questions in the chat, and when we turn things over to our questionnaire, we'll go through them. In the meantime, we're going to switch now to Marc Pound. Marc is a research scientist at University of Maryland. He's going to tell us about the PDR Toolbox, PhotoDissociation Tool Region. PhotoDissociation Region
Toolbox.
Yeah. Great. Wonderful, Marc.
Okay.
We can see things that looks great.
Great. Let me get this out of the way. All right. Well, thanks for this invitation to give a talk here about the PDR Toolbox. This is a project that Marc Wolfire and I have been working on for many, many years. It actually began as a Perl package about 20 years ago. And what it is, it's a toolkit for analyzing observations of photodissociation regions, aka PDRs, from infrared and submillimeter and millimeter telescopes like JWST, Sophia, Alma, Herschel. And it consists of pre-computed models of PDR emission and various tools to explore these models and fit them to your observations. So this is how to get more information, and I think Alice has put it in the chat. This presentation I'm giving today is actually a notebook that you can run yourself, and there's a slide version of it. And we're on Read the Docs, we're on GitHub, etc. So first, a little scientific background. What is a PDR and why should I care about them? Well, a working definition of a PDR is the gas phase of the interstellar medium in which ultraviolet radiation plays a role in the heating or the chemistry. And in particular, the UV radiation, the far UV between 6 eV and 13.6 eV is responsible for dissociating molecules. That's the photodissociation part of this. And it also dominates the heating process. We typically measure the radiation field from stars in something called units of the interstellar radiation field. So G equals 1 is just the ambient interstellar radiation field. And something like the Orion Nebula, which you can see behind me, the Orion bar, has, with the hot trapezium stars, has a G of about 10 to the 5. So where do we find PDRs? One place is something like the Orion bar, where hot young stars are shining on cold gas, and they create an interface along the edge on the outside the H2 region, where the starlight illuminates the gas and starts heating the gas. That's sometimes called the classic PDR. There's also the warm neutral medium and the cold neutral medium. So that's the generic cold gas and warm gas in galaxies. And that's illuminated just by the ambient interstellar radiation field. Both of these things are PDRs. And so you can see from this that most of the baryons that aren't in stars are actually in PDRs. So PDRs actually dominate the heating and cooling of galaxies. So this is a schematic of what a PDR might look like. So on the right side, sorry, the left side is where the OB stars are. On the right side is the cloud, and it's a sort of layer cake effect, right? So the FeV flux comes in from the left. It ionizes the gas in the H2 region, and then you get an atomic layer, and then you get a photodissociated layer, and then you get a molecular layer. And each of these layers has different physics going on, and different emission lines will arise from the different layers. So from the H2 region, you might get iron lines or recombination lines. And from the deeper regions, you'll get photoelectric heating from grains and cooling through H2 lines and carbon plus lines and carbon 1 lines and CO lines, and all these lines that emit and cool the gas. And as you go into the cloud, it gets colder. So it's hot on the edge where the stars are, and it's cold when you get where the molecules are. So how do we calculate these models? Well, Marc Wolfire does this part, and Alice, you should ask him to do his own separate talk on it. But his code produces FITS files of spectral line intensities or ratios of intensities that are distributed with our toolbox, with our Python. And those are what the package uses for the fit. We also have another PDR called Cosma Tau, and we have FITS files from those two. And so the user can choose which types of models they want to use. So very quickly, how are the toolbox models calculated? Again, this is a subject for a whole different talk, but basically, you have to do an iterative process where you step into the cloud through the deeper layers. You do the chemical balance and the radiative transfer and the thermal balance at each layer. You take into account the photoreactions and the endothermic and exothermic reactions and heating and cooling. And then what you get out at the other end is emergent line intensities and gas temperatures. And we're not the only group that does this. There's the French group, the Meudon group. There's the Cosma Tau that I mentioned. There's Cloudy. And all this stuff traces back to the classic paper by Thielens and Hollenbach in 1985. Okay, so on to some example code. Well, one of the main things that people are interested in is finding what's the external radiation field and what's the density of my gas. And so you have measurements at a bunch of different spectral lines. You put those into the toolbox. We have this concept of a measurement, and that's basically a value and an error. And you can give it virtually any unit that conforms to an intensity. We use AstroPi under the hood to convert units. And you give it the identifier to tell it what the line is. So this would be oxygen 1 at 63 microns, carbon 1 at 609 microns, COJ equals 43, carbon 2, 158 microns. You choose which set of models you want to use. So in the examples I'm doing, we'll use the Wolfire-Kaufman models that have a metallicity of z equals 1. You can also choose different metallicities. So this is an example of what is inside one of these model sets. So this is a list of all the different ratios of intensities that we have in this set. And you can see it actually scrolls off the page here. There's actually 74 in this set. And for reasons I won't go into, we fit ratios instead of intensities directly. But you put in your intensities and the toolbox will calculate, okay, what are all the possible ratios that we have models for, and then do the fit for that. So you stick these in a fitter. We can do either a least squares fitting or MCMC, and we base it on the LM-fit package if you know that. It's very simple. Stick your stuff in a line ratio fit, hit run. It runs it, tells you whether it got any errors or not. And then here's the fit result. So this is just some information on what value it got, what the error was, some information on the chi-squared values and other statistical information. That's all well and good, but what does it look like? So we've created a lot of tools to allow you to visualize your results. So I'll show 3 in order, and that basically plot the observations and the fits on this phase space of density and radiation field. So the first thing is so we put in 4 observations, and there's 3 different model ratios that are available for those observations. And so this allows you to visualize, where do my observations fit in this phase space? So there's density, hydrogen number density on the x-axis, interstellar radiation field on the y-axis. And so the contours are the models, and the red bars are your observations with the errors that you put in. So you can see here's O163 over carbon 2, 158, carbon 1 over CO, carbon 2 over C1. And we have built this on top of matplotlib. So a lot of the keywords in our plotting methods look a lot like matplotlib keywords. That makes it actually easy to use because you just put in your favorite matplotlib keyword and it gets passed on to the underlying code. And you can change whatever units you want on the axes. That's all done with AstroPi under the hood. This is a chi-squared map. So again, it's density and interstellar radiation field on the axes, and X marks the spot. That is the best fit for the data that you put in. And that's a density of about a few times 10 to the 4 and a radiation field of a few hundred. You can also overlay all the data on a single plot. So this is something that our users have tend to like. You see these a lot in the publications that use our package. So we call this an overlay plot. So it's just basically all the data overlaid on the phase space, and you can see this is where they all intersect is where the best fit is. Now that was with a single pixel, but you can also do this with maps. So if you have a map of these quantities. You can fit every pixel in the map. And this is an example with some data from Jameson et al. 2018. So again, you put in measurements, but in this time, instead of putting in single values, you give it FITS files. Choose a model set. In this case, we have a special model set for the Small Magellanic Cloud, which is where the data came from, and that's a low metallicity data set. You do it, it runs at every pixel, and voila, you get a map. Let me, oops, go down a little bit on this. So now you have a map in space of, this is a map of the density, and this is a map of the radiation field. So this is really nice. You don't have to do things pixel at a time. You just give it FITS files, let it run. This takes on my laptop this map, which is about 5,000 pixels, took about a minute. Another thing we can do is fit molecular hydrogen excitation diagrams. Now, instruments like JWST measure all sorts of rotational and row vibrational emission from the H2 molecule, which is a dominant molecule in PDRs. And the common way to understand what's going on is to use excitation diagrams, which plot the energy of the transition versus the column density. And I'll show an example of that. Again, it's just like the other fitter. You make measurements, you instantiate a fitter, you run the fitter, and you look at the results. So that's just what I said. But here's it visualized. So you create a plotter, you give it the fitter, and you tell it that you want to see the fit. So the blue dots are the data. So these are different J transitions of molecular hydrogen. And the common way is that you fit this with two temperatures. So there's a hot gas component and a cold gas component. And the cold gas dominates at the low energy end, and the hot gas dominates at the high energy end. And so you get this curvature in your data. And so we run the fit, we fit both the low temperature component and the high temperature component, and also get the total column density out. Now this looks pretty good, but you can see like there's some jaggies in here. Maybe we can do a little better. Well, it turns out that there's both ortho and para H2, and you can also fit that as part of this excitation diagram fitting. And if you allow the ortho to para ratio to change from its canonical value of 3, you see that every other value with ortho to para only affects the odd J transitions. Then the black triangles are the adjusted data, and you can see that the temperatures are much better fit. So before that was plus or minus about 100 on the temperature, and now it's plus or minus 1 Kelvin. And the column density comes down a little bit. So as with the other fitter, you can actually do this on a map. If you have maps of H2 emission, you can run this fitter and get an excitation diagram like this at every single pixel. And we have an Explore tool, which I won't show you, but it allows you to click on the map and it pulls up the fit at every pixel. We also have something called phase space plots, and this was a feature that was actually requested by our users, by the SOFIA feedback team. And this allows you to plot ratios of emission or intensity on each axis and see where the quantities of interest lie. So in this case, this is for the ionized gas. You plot the ratio of 2 iron lines versus the ratio of 2 other iron lines. And that spreads out in the phase space, that spreads out the electron temperature and the electron density. And then you can plot data on top of that and see, okay, what's the temperature and density of this gas? And we've tried to make this very easy, that in how you can create and manipulate these plots. So, you just give it the identifiers as strings, and the toolbox will figure out which models these refer to. And you can do things like, clip the axes and zoom in and choose different colors. By default, I choose a colorblind friendly palette, but you can change all that. It's all matplotlib under the hood. You can do a lot of different things. You can change the units on the axes if you want. What else? Let me actually go, since I have a few seconds left. You can also make isocontour plots. So this is another way of inverting that plot that I just showed you. So in this case, you can put, say, electron temperature on the x-axis and the ratio of two lines on the y-axis, and plot electron temperature, sorry, density on the x-axis. And similarly, you could flip that. You could plot temperature on the x-axis, and you get contours of density. So there's a lot more that the PDR Toolbox can do. There's a lot more coming. We'll be doing, right now, one thing that Marc is working on is models where you have different viewing angles. So that affects what the emission line, the emission intensity you see. And, we're not always looking at PDR straight on. So that's coming out in our next release. We'll be doing more metallicities, more lines. We'll be doing a model exploration tool. So, you have all these different models from different groups. How can you tell what's in each kind of models? You'll be able to take models from different groups and compare them with this tool. We'll be doing more robust fitting in the image plane. Sometimes you get places where the fit can be sort of one of two different answers that are equally good, and so you want to do some sort of regularization technique. Anyway, all this is coming in the next 18 months, as long as Elon Musk doesn't pull our funding. And I will stop there. Thank you very much.
Good image to stop on. So thank you both, Marc and Rhys. I'm going to turn things over to Sam, who's going to handle the questions. We have about 15 minutes left in the Zoom time.
Yeah, thanks, Mike, and thanks to both our speakers. Both really good talks. So yeah, if you if you do have questions, please feel free to put them in the chat, or if you raise your hand, I can also see you. I think, yep. So there is one question already. This is for Rhys. And Mike asks, has anyone tried using FRELLED for simulation data, doing volume renders of 3D data sets from a hydro simulation?
Oh yeah. You can do time series. You can just simply tell it that I want to use a time series. So as long as you provide the files with a simple given extension, so _0000001, etc., it can be set to automatically load those files sequentially, render them, and save the output to a PNG. It's really quite fun to see the volume renders done in that way. But the isosurfaces also look, and for example, for jellyfish galaxies, that looks really weird to see these writhing surfaces. It's really fun to plot. I don't know if it helps, but they do look nice.
Sounds good. Yeah, thank you. While we wait for more questions, I also had one question for Rhys. So one thing I've heard about Blender is that it's very computationally intense to use. Have you run into any issues running it on just like a personal laptop or anything?
It's computationally intensive depending on how you use it. So the way that FRELLED works, the back end, is that each slice of your data is effectively cut into slices. So for example, channel maps, which are rendered as ordinary PNG images. So if you load them onto a textured plane in Blender, or a mesh, sorry, then you can load, a few thousand of these before you really hit a wall. And it is kind of a wall, though. Once you go beyond that, performance really drops off a cliff. But beyond that, things are really quite good. So that there are definitely limitations. I do have possible workarounds that might be able to extend this limit considerably, but this is requires a lot more investigation to make sure this will actually work in practice, rather than just the quick tests that are being experimented with.
Okay, great, thank you.
Mm-hmm.
And then I so we have one comment, I guess. Brittany says, I have used Blender for artistic projects, so it's really cool to see it being used in this way.
Thanks.
And I agree with that. It's very cool stuff. I have a question for Marc. So you mentioned that sometimes the observations are viewing these PDRs off axis, but that the PDR toolbox is not yet maybe equipped to handle that. I'm curious what happens, I guess, if you try to use your tool on a
so the models, so Marc's models are plane parallel models, where you're viewing face on, and so all the radiative transfer is done assuming that line of sight. And so if you have observed something not face on, you're going to be intersecting the layers of the PDR at a different angle. And so the emergent intensities are going to be different than if you were looking at them straight on. And so if you fit that with a straight on plane parallel model, it's not going to be quite right? It depends on how far off that angle is. And there are some heuristic corrections for that are in the literature. And that's what most people use. So they use our models, and then they apply these after the fact corrections. But the better thing to do is actually calculate models at different angles, and then allow people to choose angles. Marc, did I say that right?
Yes, perfect.
Okay, great. Thank you. Thank you. So I have one other question for Rhys. Some of the images you showed, when you zoomed in enough, you could see the pixels, individually.
Mm-hmm.
And I'm wondering if FRELLED has any capability for doing some kind of interpolation to sort of smooth over those things.
Yes, it's not built in, but it could certainly be enabled relatively easy. You can enable this mapping in Blender, so you get a very much more interpolated smoothing. I personally don't like that. I prefer to keep it to what the raw data actually is. But certainly in some cases, if you want to make a nice visualization, this definitely helps.
Okay, yeah. Thank you.
Mm-hmm.
We seem to be good, Sam. It's okay if we wind up a little early.
Okay.
Thank you, everyone, both our speakers. Thank you, our audience as well. We have one talk already confirmed for next month. Nikhil Saran from Nordita on Redback Bayesian inference software package for fitting electromagnetic transients. We have one more tentative one, which we'll post shortly once it's all confirmed. And we do encourage everyone to continue to suggest talks, and that you take a look at the previous vast sessions which are recorded and up on YouTube. And so you can learn about some of the fun projects that we've heard from previously. So I think we're good and we can stop the recording.
Everybody.